This video is part of CAE Associates ANSYS e-learning series. CAE Associates is an engineering consulting firm in Middlebury, Connecticut, specializing in finite element analysis and computational fluid dynamics. We have been an ANSYS channel partner since 1985 and have developed our ANSYS e-learning series to help you maximize your software investment. Please visit our website, which includes an extensive resource library with over 250 items and counting in an easily searchable area. We also invite you to visit our Engineering Advantage blog, where we share insights from our many years of performing engineering analysis. CAE Associates also offers an extensive schedule of ANSYS courses taught at our Middlebury office. If you need help deciding on the best courses to take for your application, visit our CAE University page. The complete library of e-learning recordings is available for viewing in our resource library and also on our YouTube channel at youtube.com/CAEAI.
For CFD analysis. And why we're interested in this? Because very often a flow domain is quite complex, and we also understand, if you want to generate hex mesh for a very complicated flow domain, like clearances, seals, highly curved surfaces, to create hex mesh is going to be quite challenging. It very often is a chore. You could spend a lot of time, a large amount of time just to generate a good hex mesh. So when we are in this kind of situation, the common approach would be like, try an easiest meshing method. In workbench meshing, we all know this, right-click, generate mesh, and that will give you something to start with. And most likely, what you're going to get is a tetrahedron mesh. If you insert prism layers, and you will have a combined TET plus prism elements for flow analysis. And that is very, very common and convenient to use and, easy to generate. So it gets quite popular doing this. And most of us probably have a habit, just right-click, generate mesh, and not worry about much else. So the good and bad, right? Good is it's very convenient. You can get a mesh, relatively quickly. But the downside or disadvantage is tetrahedron elements is a pretty isotropic element. So it does not stretch well, does not pave, the clearances gap well. And because of these reasons, and sometimes you're going to end up with excessive amount of element count, just because when you try to resolve a tiny, tiny gap or engineering clearances, and you have to end up using a very, very small tetrahedron element and use quite a few of those to fill in those regions, and you end up with 10, 20 million elements. So in these situations, is there a possibility that we look for hex meshing and through some method that is offered in workbench meshing module, and also looking into the possibility, saying, we can somewhat, slice and dice the flow domain into different parts, and then we can look into generating hex mesh. In general, in CFD, hex mesh, like FEA, hex mesh probably offers the best, accuracy and solution, at least among the numerical diffusion. So if you have hex mesh, that would be great, and that offers you all the benefits that you can get from using the elements, hex mesh elements. You have a less element count, and you have a shorter CPU time, and probably have a better solution accuracy. So let's get into it. Get out the PowerPoint and get back to what we're talking about today. So first example that we want to look at is a mixer, right? I have two inlets and an outlet. And like we all know, in this case, I just simply set up default. There's nothing set up except I set up the prism layers. I asked the program to generate default prism layers. To generate the mesh, like I said, right-click, generate mesh. And by default, Workbench gives us tetrahedron elements and coupled with prism layers, which is not bad. But in case I don't like this, look at the elements. It's huge, right? and it's not going to capture what's inside this tank. I can insert an element sizing. I'm going to pick the entire volume and make it like 5 inches. This is a very large domain. And I can generate the mesh again. So in this case, you will see I have a much better resolution for fluids analysis. The elements are much smaller, and if we look at the cross-section, I have a prism layout throughout, and I offer enough element resolution in the middle of the tank to provide the mixing resolution, so forth. So this is default because this domain, this geometry, is not sweepable, and there's no other way to create sweep mesh and so forth. So what do we do? What do we look at the hex mesh? Workbench offers a method. It's called MultiZone. This was available like 2 releases ago, and since then has made some improvements to this. So I'm using the same size setting and using MultiZone, right? Just to give it a try, it creates a majority of the hex elements with some mix, in with some of the small amount of tetrahedron on the surfaces, right? So right now, if you just say generate mesh, and you will see if I use the default MultiZone, I'll get back with a message saying cannot be done. And you notice the error message. It cannot be done because in this case, and the measure cannot place all the hex elements into this tank, right? And imagine you're a bricklayer. You want to put in bricks into this tank. And what do we do from here? There are several options. The options I want to talk about. There are several options, using MultiZone. Don't stop at the first try. Give the other options, a go just to see if you can be successful. So in MultiZone, there is an item called free mesh type. This is the feature. By default, is not allowed. So MultiZone meshing method will create all hex elements. In this case, it's probably not doable. So there are options. In the regions, the measure cannot place hex elements. That means you cannot lay bricks into the gaps or a zone. I have option to choose in these regions. I want to use tetrahedron elements, hex dominant or hex core, right? And so in this case, let's say pick hex core, for example, to see how it goes. And I have MultiZone meshing, and I pick hex core for those regions, that the measure has difficulty to place all hex elements into. So in this case, and you see how the mesh is going, and you will try to patch to generate as many hex elements as you can. And now you see on the surface is all hex, and I also have very nice inflation layers on the solid surfaces. And the only difference is now if you look at the cross-section, right? This is what it will do. In the middle of the tank, which is where the 2 fluids going to be mixing, and I have wonderful resolution of all hex elements. In between the boundary and the hex core, and where the program failed the first try because it just cannot place all hex elements, and now this time in those regions, it's being filled in with a layer of tetrahedron. So overall, the mesh is pretty good, and it offers the combination, the advantage of most of the hex elements in this tank with just a small portion of the tetrahedron elements. So when you use MultiZone, and there is always this opportunity and explore MultiZone meshing method. If it works, great. If not working at the first try, go through these couple options right here to see what you get. So this is a way looking at generating hex mesh, for a flow domain that is not easily, sweepable and or 2D, almost like a slab or cylindrical type of geometry. And so that's quite helpful. Okay. The next example I'm going to present is, again, another scenario that we'll very often see in fluids domain, right? And I have a geometry. Right here you can see I have a sink gap here. And on top of the sink gap, I have a piece of a cavity. But the cavity does not extend all the way through the gap. So this is the flow domain. If you right here to see, shows sweepable body, and there's nothing sweepable, right? It's a non-sweepable body, and it's got the combination of tight gap and a cavity and so forth, right? So if I go ahead to generate a default mesh, what it's going to be like? Even you have the setting to CFD, and it's pretty rough, and you're pretty sure that there's no way that you can resolve the flow gradient in this gap, right? You have pretty much one element, one huge element across. So by using the default mesh, let's insert, just activate this body sizing that I pick. I literally just assign a small element sizing, try to resolve the flow in the gap, and you can see even that is a little big, but we'll see how the measure can do. So to resolve the flow in the gap and also in the cavity region, so by doing that, again, generate mesh, and we see the default measure, workbench measure is going to use the tetrahedron plus prism elements to fill in this flow domain, which include a tiny gap and a cavity and so forth. It takes about a minute or two to generate a mesh for this case in here. So while the measure is working, let's look at other alternatives. Right? So we understand the flow domain now, and now let's look. What if, let's take advantage of the design modeler feature. On this flow domain, excuse me, we can divide the flow domain into 3 parts. In this case, I form a common part for all 3 flow pieces. So I kind of divide the flow domain into the cavity part and the majority of the annulus region and the region connected to the cavity, the annulus region connected to the cavity. So in this way, all 3 parts becomes sweepable. Okay. And the show of hand here, by looking at the mesh setting and so forth. Let's jump back a little bit to see if that one is done. And it's still working, and probably will be done in 30 seconds or so. Okay. Do you have any questions at this point? Okay, so it's nearly complete for the meshing process. As you can see here, even with the combination of convenient tetrahedron plus prism elements, because of the challenges in meshing flow domain and a tiny gap, coupled with a couple of irregular parts, and it has some sort of it takes a bit to generate the elements for that. This is about done. It takes about 3 minutes, and we're almost there. So in this setting, now you see the meshing is complete, right? I mean, it did a great job. I end up having 5 elements, 5 prism layers inserted in next to the boundary, which just like what I specified for the default inflation layers, controlled by the program. And by using this mesh element size, I could resolve the gap quite nicely. And you also notice, because like what I say in the beginning, the isotropic nature of tetrahedral elements, I end up with a large amount of elements in the axial direction of the flow domain, which is not necessary. And because of the measure needs to resolve the gap, it has no choice but to use tiny elements in the axial direction. So in the circumference direction, if you tabulate the element counts, I'm looking at the several hundred, probably approaching, like 700-800 for the elements in the circumference direction, which you probably don't need that. So if you look at this case, and you can see the tally here, the total element count is 1.67 million, right? And to resolve this, if you want to have a good flow resolution, this is what you have to do by using, default, tetrahedron plus prism method, right? And now, let's look at our example right here. Since now we divide the flow domain into 3 parts, so here, all 3 parts become sweepable. If you look at the meshing setting that I have here, I set up a sweep mesh, okay, for majority of the circumference region, and I have set up edge sizing. I can control exactly how many elements that I like in the circumference direction, right? In this case, I have 220 elements, and I have edge sizing to control how many elements that I like in the axial direction. So when they become sweepable, you can set these element sizing, because I have 3 parts now instead of 1 big flow domain. I can set these control easily for the 3 parts. And then I set up a second sweep method for the tiny piece of the circumference region directly underneath the cavity, right? And I set the edge sizing, which is roughly have the same edge spacing as the rest of the circumference that I just set for these edges. And I have the number of elements that I want in the cavity region. And lastly, I have the number of axial elements in the cavity region. So all I did is just divide the flow domain into 3 pieces, and because now they're all sweepable, I define for each region, each edge and each line, what element sizing that I want and how many divisions that I want. I can control this, precisely, and right-click, say Generate Mesh, and you see we talk about the previous mesh tetrahedron plus prism layers. It took about like 3-4 minutes to generate, and here it's done in about 10 seconds. And the measure, you can see here, it's all hex elements, okay? All hex elements, and I generate enough resolution. I specify like 10 elements across the gap, and 10 elements in the gap region. And because all 3 pieces, all 3 sweepable bodies are now reside in the same part, right? And it's defined here. So you see all these mesh elements are conformal across the boundaries of each 3D flow volume, each one of these part, each one of these 3D volume. And when you bring those into solver, regardless of Fluent or CFX, they will be recognized as the flow-through mesh. So you don't have to worry about interface problem. So that's one nice thing about, you can take advantage of this feature, to divide the elements, to divide the flow volume into 3 parts and form a new part, so they have conformal elements across the boundary. So that gives us an idea. This can be done. Just needs you to look at the flow domain or the problem that you want to solve to see if there is any reason or there's any possibility to slice and die your flow domain into different pieces. Now let's look at the total element count. So in this case, we end up with 140,000. Right, 140,000 compared to the tetrahedron plus prism element, that is 1.67. It's only a fraction, less than 10% of what is required of the default or using the tetrahedron plus prism element. So it's a very wonderful trade-off, right? I just do a little bit of work to cut the domain, flow domain, in 3 pieces, and have a very nice and easy way to create a nice hex element in this analysis. And in addition to that, I'm probably going to get the very accurate results, with least amount of numerical diffusion in the gap region in terms of flow solution, right? And the next scenario is the same situation, very similar, but instead of making them into one single part, I slice and dice the flow domain into the same three flow volumes, but they are of different parts. This is a situation when you find the conformal mesh is difficult to generate. Sometimes workbench needs to consider all these parts connected in the same part, all these volumes connected in the same part, and it needs to generate conformal mesh across. Sometimes you probably run into difficulties. So if that's the situation, you don't have the luxury to generate conformal mesh. And here's the alternative that you can consider. You make the 3 parts, separate. Now I have 3 separate volumes, right? But all 3 parts, all 3 flow volumes are all sweepable. So I'm doing the same thing to specify a sweep method, first one, a second one, and the third one, because now I have 3 separate flow volume, and each one needs to have a mesh generated. And I have a similar setting to set up edge sizing, okay? Very similar to the second mesh. I just set up, I pick and choose the edge sizing to set up a number of elements that I want for each sweepable flow volume, and that will be that section, and that will be the elements, okay, in the radial direction, and also in the cavity. And the last one is that will be the number of elements for the cavity in the circumference direction. So I set up pretty similar way, very pretty similar way to previously in terms of number of elements for each flow volume. And all I need to do is just right-click, generate mesh. And so Workbench is doing this. You can see the mesh is done almost instantaneously. Okay, and I have all hex mesh for 3 parts. Instead, the differences between this one and the last mesh is now they are in 3 different flow volumes. So Workbench is no longer, required to match the element size across the boundaries of the 3 flow volumes. So you see the mesh element is not conformal. Okay, so it's not conformal. So in this way, if Workbench has difficulty to generate conformal mesh, this is an alternative method to go. And you still end up with a very nice hex mesh, and the total element count is a bit less. It's 127,000 because Workbench does not even worry about to match the element size and shape across each one of these boundaries. But keep in mind, since we have 3 separate flow volumes, once this is done and you take the mesh into either Fluent or CFX, and you need to generate in Fluent is mesh interface, in CFX it's probably a domain interface. You need to connect them together. Otherwise, for these non-conformal elements across a flow domain or flow boundary, if you don't connect them, they will be recognized as a wall. So you kind of prevent flow from going across these boundaries. So if you're not careful to set up the mesh interface or flow or domain interface for Fluent or CFX. Okay. So in summary, we can indeed, if you have a complex flow domain, and it can be difficult when especially when you run into engineering clearances, and curved surfaces, it could be problematic and time-consuming to generate a mesh. And if you use default tetrahedron with Prism, nothing wrong with that, but you could end up with a large element count. And for a complex problem, I've seen is easily you could end up with like 20, 25 million elements, right? Which could take a long time to solve, even for steady state. If you want to work on a transient problem, and good luck with that. And you could take, like several weeks to complete a transient analysis on a large element problem. So look at your flow domain to see if there any possibility, by cutting and slicing and dicing into different parts, into different sections. So take advantage of the workbench meshing methods, try, MultiZone, or, find out any parts that's sweepable and apply those methods to most, suitable part and get the mesh, so you have a method, when you're doing this, sweepable or MultiZone, you can get hex elements out of it, which will help you to reduce the overall element count of, ultimately your overall CPU time substantially for some of these problems.